Hey, what's up? Welcome back. Patrick here from All Things Mathematics, and moving on to the next example dealing with linear algebra. So we have to figure out what value, or sometimes values, of m makes this system here, this matrix, three different things, three different cases. So consistent and independent, meaning that it has one solution; inconsistent, meaning it has no solutions; or consistent and dependent, meaning it has infinite solutions. And just as a quick review, if you remember, the solutions can be basically in two categories, right? So they could be either inconsistent, right, which means that there's going to be no solutions, or they could be consistent. And then if they're consistent, if there is a solution, well, there can be two different kinds of solutions, right? There can be an independent consistent solution, which means that there is one solution, or it could be dependent, meaning there's going to be an infinite amount of solutions, right? So this is how I like to sort of categorize the different kinds of solutions that you can get from linear equations right here. Now, in terms of how the matrice is going to behave in each of these, if a solution is inconsistent, meaning if there's going to be no solutions, what's going to end up happening is you're going to have a row where on the left side it's going to be all zeros, and then on the right side there's still going to be some kind of constant other than 0. Right? And that can't make any sense, right? 0 times anything can't give you some kind of constant, right? And so if you end up getting something like that, then you know that the system is going to be inconsistent, or there's going to be no solutions, right? Now, an independent solution is when you're going to end up having x is equal to some kind of constant, right, for all the rows. Okay, then there's going to be only one solution. It's going to be a consistent independent solution, right, if you end up having just x equaling a constant. And then the solution is going to be consistent and dependent, or there's going to be an infinite amount of solutions if you ever get a full row of zeros, meaning that you have like 0x, so you'll have all zeros on the left side and also on the right side. The constant is going to be 0. Okay, so those are the different categories that can happen here. That's what we're going to be looking for in this matrix. So let's maybe write these here. So if there's going to be one solution, it's going to be if we're able to get just an x equaling a constant, right, or any kind of constant in front of the x other than 0, right, but then you could just divide both sides by that constant and get the x by itself. It's going to be inconsistent, no solutions, if you're going to have 0 x equaling some kind of constant other than 0, and then infinite solutions if you get a row of zeros, 0x equaling 0, like that. So what we want to do with this matrix here is notice it's not in row reduced echelon form yet, or reduced echelon form. What we want to do is take care of this third row here, and I want to get rid of this m value, right? I want to make that equal to a 0, and so that third column will have a pivot right here in this entry. And so how can I get this m to be a 0? Well, what we could say is we could say, okay, our new row 3 is going to be our old row 3 minus m, that's the constant we're multiplying row 2 by, right? Because if you notice, what's going to happen then is we're going to have m, this entry, minus m times the entry in row 2, which is 1. Over here, right? This is the column I am focusing on, because again, I'm trying to get this m value to be a 0 here, right? And so multiplying here by 1, notice that we are going to get that 0 that we want, like that. Okay, so this is the formula here that we are going to use. And so if we do use that formula, what is the new matrix that we're going to end up with? Well, notice that the first row is not going to change, so we could keep that the same. Also, the second row, actually, you know what, let's maybe make some more room here. I'm not going to close off the matrix yet. So The second row is also not going to change, so we'll have 0, 1, 2, 3, but the third row is going to change, right? So we're going to have 0, as I just showed here, m minus m times 1 is just 0, so we're going to end up with a 0 here. Here we're going to have 7 minus m times 2. So it's actually going to be an expression 7 minus 2m that we're going to get over here, 7 minus 2m. And then over here, we'll have 2 minus m times 3. So we're going to have 2 minus 3m. Right here, this is going to be 2 minus 3m, like that. And so notice that from here, we can now go through each of these cases and see what m value for these is going to give us these cases. Now, first thing I want to mention is that notice that you can't have an m value that will make both of these 0, right? Because notice that 7 minus 2m, okay, this entry here is going to equal 0 when what? When 7 is equal to 2m, or when m is equal to 7 over 2. While this entry here is going to be 2 minus 3m equals 0. When's that going to equal 0? Well, when m is 2 over 3. So notice an m value of 2 over 3 makes this 0, and then an m value of 7 over 2 makes this 0. And so you can never have both of these simultaneously being 0. So what does that mean? Well, what it means is that we can never have this case happen, right? We can never have a consistent and dependent solution. So this case here is going to be impossible, right? Again, because there's no m value that can make both of these 0 at the same time simultaneously. And in order to have a consistent and dependent solution, or infinite solutions, right, we have to have 0 on this side and 0 on that side. It has to be a full row of zeros. Now, what about this second case, this one where we have an inconsistent solution, meaning that there's no solutions, right? So where we have 0x is equal to some kind of constant, well, what value are we going to get as 0 here? 7 over 2, right? So notice that if m is equal to, let's write the solution here, 7 over 2, what's going to happen is we're going to end up with a 0 here, and then on this side we're going to have 2 minus 3 times 7 over 2, which I'm not sure what that's going to be. 4 over 2 minus, doesn't matter. Basically the point is it's not going to be a 0, right? And so notice that if m is 7 over 2, then we're going to have zeros here on the left side, but then some kind of constant, which is going to be negative 7 over 2 if I did the math there correctly. Yeah, it's going to be, or sorry, negative 17 over 2 on the right side, right? And whenever you have something like that, zeros on this side and then a constant on the right side, you know you're dealing with an inconsistent solution. Okay, so for this particular matrix, or this particular system of equations, that's going to happen when m is 7 over 2. And then for this one, to have a consistent and independent solution, or just one solution, it's basically going to be any m value other than 7 over 2. Right? So any m value other than 7 over 2, including 2 over 3, because if we plug in 2 over 3, what's going to happen is we're going to end up with some kind of constant here. So what would that be? 7 minus 2 times 2 over 3, which is going to be 7 minus 4 over 3, which is going to be 17 over 3. So we'd end up with 17 over 3 over here, and then over here we'd end up with a 0. Well, what is that going to mean? It's going to mean 17 over 3x3 is equal to 0. So that means x3 is just going to be 0, which is fine, right? That's a potential solution that we can have if that m value is going to be 2 over 3. Okay, so you can have this being a 0 here, and if this is some kind of other constant, okay, then the solution is consistent and independent, right? There is going to be a solution, and in that particular case where m would be 2 over 3, the x3 would be 0. And then any other value, right, other than 7 over 2, any other value, you're going to get some kind of constant here, which again is going to give us some kind of solution for x3. It's going to end up being some kind of value. And so all of these, basically x1, x2, and x3, is going to have a consistent and independent solution. They're going to have some kind of value, which makes the whole system have just one solution. Okay, so hopefully you caught all of that. Basically, if you remember the different categories for the solutions, right? The two general categories, inconsistent, consistent. Inconsistent means 0x equaling some kind of constant, and then you have, under the consistent category, you have independent or dependent. Independent means there's one solution, right? So if you end up just having a constant equaling, or a variable x equaling some kind of constant, and then you can have an infinite amount of solutions, which is consistent and dependent. That's if you have a full row of zeros, which is impossible in this particular case. If m is 7 over 2, you have an inconsistent solution because this is going to be 0, this is going to be some kind of constant. And then any other values other than 7 over 2, you would end up with one solution. All right, so hopefully that made sense. You may have to rewatch that again. Did my best to explain it, but yeah, hopefully you understand how to go through the different cases if you do get a question like this, figuring out how that constant m can give you these different categories of solutions. And that is the end of the video. Hopefully you enjoyed that. If you want to find more videos like this, you can go to my website, allthingsmathematics.com. Over there, all my courses are organized for both high school and university. All the videos are organized by chapter. Also, if you have any questions, you can hit me up. My contact details are also on the website. Enjoy your day, and I'll catch you in the next one. Peace out.